Welcome to the Building Better Batteries webinar series that is sponsored by Thermo Fisher Scientific. My name is Christina Pogge. I'm Senior Manager for our Science and Industry Content Strategy team at Wiley, and I will give you a quick overview of what you can expect to learn today and in the coming weeks. This is an 8-part webinar series that explores the intricate process of battery development, from materials research to cell manufacturing. This series aims to identify unmet needs and prevent failures while maintaining high-quality assurance standards. You learn about essential topics and ensure the quality and longevity of batteries, gaining insights into advanced techniques and methodologies, about diagnosing battery issues, understanding failure root causes, and implementing preventive strategies. Today, we will be presenting 2 analytical solutions for assuring the quality of electrode slurries and coatings. First, Annika Völp will review rotational rheology for QC and research on battery slurries and dry processed electrode films. In the second talk, Alon Vaisman will present advanced inline metrology.
As a company, Thermo Fisher Scientific has a clear mission: to enable our customers to make the world healthier, cleaner, and safer. Let's break that down a bit further. Healthier. Thermo Fisher Scientific contributes to human health by empowering our customers with advanced technologies and expertise. This allows them to develop breakthrough medicines and diagnostics that improve lives across the globe. From life-saving treatments to innovative diagnostics, our customers rely on us to help them achieve the impossible. Cleaner. In the fight against climate change and environmental degradation, Thermo Fisher Scientific provides the tools to understand these challenges and develop greener solutions. Our technologies help ensure the quality of air and water, essential elements for life on our planet. Together with our customers, we are committed to preserving the environment for future generations. Safer. From detecting contaminants in food to solving crimes and identifying threats, we help our customers protect their communities. Our instruments and solutions are designed to keep people safe, and together, we are determined to make the world a safer place. At Thermo Fisher Scientific, we are not just creating products. We're enabling our customers to make an impact on the world. Thermo Fisher Scientific is the global leader in serving science operating in 170 territories with over 140,000 colleagues, generating over $40 billion of revenue, and they reinvesting almost $1.3 billion annually in new products. Within the battery market, Thermo Fisher Scientific partners globally to deliver advanced integrated solutions from the research laboratory to the battery production line that ensure material quality and accelerate improvements in battery production efficiency. Thermo Fisher Scientific serves the battery value chain with advanced analytics from research to recycling, with market-leading technologies in spectroscopy, electron microscopy, and mass spectrometry. Within this webinar series, we will be focusing on the mining and mineral processing, battery component materials QC, and production pieces of the battery manufacturing value chain. There are many dynamics affecting the battery industry. Firstly, to compete in the battery marketplace, new battery manufacturers need to get to high yield, high volume manufacturing fast. Poor quality costs material, production volume, and time. You must prioritize quality. Saving money on metrology is seldom rewarded with anything but headaches. Companies are prioritizing quality. Secondly, new battery companies are investing in innovation. There's little chance to catch up with established battery manufacturing companies in China by repeating what they do. Companies are looking to leapfrog. They are investing in advanced technologies early to facilitate faster product development and troubleshooting of quality failures. Thirdly, new battery companies are thinking globally. They may have a laboratory and pilot line in Mumbai, but they will want to replicate that capability as they scale their operations in Europe and North America. Consequently, they need global partners who can support their growth in every territory.
Our speakers today include Dr. Annika Völp, a process application specialist at Thermo Fisher Scientific, And Alon Vaisman, Senior Manager, Strategic Business Development at Thermo Fisher Scientific. So I will now hand it over to Annika.
Welcome to my presentation on rotational rheology for QC and research on battery slurries and dry processed electrode films. So first of all, I want to start with an introduction. What is a rotational rheometer? Rheology is the science of flow and deformation of matter, and there are different techniques and instruments available to study the flow properties of various materials under different conditions. A very versatile device for rheological investigations of a broad range of samples is a rotational rheometer. Rotational rheometers are used in many different industries for quality control of incoming raw materials, intermediates, and final products, as well as in the development of new formulations. Information about the rheological behavior can help to assure that a product performs well in a given application or that it can be processed in a certain way. A rotational rheometer usually works in the following way. The sample is filled into a measuring geometry and the rheometer applies a defined shear stress or shear deformation. The response of the sample to such mechanical excitation is detected and used to calculate rheological parameters. A modern rotational rheometer can apply shear stresses or shear strains in form of a continuous rotational motion as well as a sinusoidal oscillation. Measurements in oscillation mode are usually used to obtain detailed information about viscoelastic properties of the material. In a rotational rheometer, most measurements are performed under well-defined conditions that include precise temperature control and consistent flow conditions throughout the entire tested sample volume. A rotational rheometer usually consists of the following main components: a measuring head that applies the shear stress or the shear deformation and measures the response of the sample. An accurate lift mechanism that moves the measuring head and the upper part of the measuring geometry into the correct measurement position. A measuring geometry that holds the sample and transfers the torque or the motion generated by the motor to the sample. And a temperature control module that provides defined temperature conditions and supports the lower part of the geometry. I defined some basic rheological terms used in the following. The viscosity is a measure of the resistance of a material against flow. The dynamic viscosity is defined as the ratio between shear stress and shear rate in a material flow. The shear stress is proportional to the force acting onto the material or the rotor torque in a rotational rheometer. And the shear rate is the material deformation per time unit, so the rotational rotor speed in a rheometer. A fluid acts like water, is called Newtonian if the viscosity is independent of the shear rate. Shear thickening fluids like starch in water exhibit increasing viscosity with increasing shear rate. And shear thinning fluids like ketchup exhibits decreasing viscosity with increasing shear rate. The viscosity at the limit of low shear rate is called zero shear viscosity. Some materials behave as elastic solid at low shear stresses and as a viscous fluid at high shear stresses. Those materials are called viscoelastic. The transition point, the minimal shear stress required to cause irreversible plastic deformation and flow, is called the yield stress. The onset of flow is hence related to a structural breakdown in such material. The time dependence of the structural breakdown is called thixotropy. It can be measured by applying different steady shear rates onto a material and observing the temporal drop and recovery of the viscosity. Here we outline the manufacturing workflow of lithium-ion battery electrodes, emphasizing the crucial role of electrode slurry rheology as a quality parameter. Rheometers serve as widely adopted quality control tools, particularly for the characterization of the viscosity shear rate dependence of both anode and cathode slurries. This characterization is essential as it predicts dispersion stability during storage and slurry and the behavior during the coating process. Rheometers are utilized for various purposes: ensuring the proper mixing of a slurry for quality control, facilitating the development of new formulations, and for tailoring the slurry rheology to optimize the coating process. Widely spread spindle viscometers are commonly used for quality control, but they only measure apparent viscosities. Rotational rheometers, on the other hand, are essential for obtaining real viscosity data due to their ability to provide a defined flow field throughout the whole sample. Thermo Fisher Scientific offers a whole range of different rotational rheometers, from compact quality control instruments to high-end rheometers for research and development. Those instruments differ in the width of the available measuring range with regards to the torque and rotation speed, as well as in the available accessory portfolio. Which of these instruments is right for your application depends on the type of the sample and the kind of experiments you want to do. All our rheometers can be equipped with temperature control units that generate then absolute viscosity data, and they can perform shear rate sweep tests to produce complete flow and viscosity curves. In addition to our broad analytical instrument portfolio, we provide a wide range of laboratory chemicals, including fine chemicals, solvents, and standards to support battery research and development, quality control, and scale to up to manufacturing. We offer a complete line of chemical solutions, including formulation chemicals and materials for anode and cathode, as well as electrolytes, such as lithium salts and a wide range of pure metals. Then there are organic chemicals and solvents like NMP and diethyl carbonate, but of course also the general lab chemicals are there, like high purity acids, isopropanol, acetonitrile, methanol, just to name a few. And separators and binders like acrylic acid or PMMA, as well as PTFE. To browse the complete portfolio of our products supporting battery research and manufacturing, use the link at the bottom of the page or the QR code. So electrode slurries usually show a so-called shear thinning behavior, which means the viscosity is decreasing from high values at low shear rates to low values when the shear rates are increasing. For many complex fluids, including electrode slurries, this is a desired behavior because high viscosities at low shear rates or at rest show sedimentation or slow down the sedimentation or aggregation effect significantly, leading to a better shelf life and less need for agitation during storage. High shear rates, on the other hand, occur when the material is applied to the current collector foil via the slot die coating. In order to achieve a quick and homogeneous coating process with a constant layer thickness, the sample viscosity needs to be within a certain range and can neither be too high nor too slow. So complete viscosity curves spanning from low to high shear rates are therefore extremely useful to predict various important aspects in the process cycle of an electrode slurry. This example here shows the viscosity versus shear rate of an aqueous LFP-based cathode slurry with 43 and 50% solid content, respectively, mixed with a lab-scale twin screw extruder at a different screw speed, namely 120 and 1000 RPM. Viscosities were measured in a Harker mass rheometer with 35 mm parallel plate geometry in a steady rotational shear deformation. With increasing solid content of 7%, the viscosity increases by more than a decade at a shear rate of 1 reciprocal seconds. However, the viscosity of the slurry with 50% solid content can be reduced significantly by applying higher shear forces in the mixing process with the higher extruder screw speed. This effect is attributed to a broadened particle size distribution, as emphasized by the SEM images that you see here on the right, of the dried slurries when they were coated. A broader particle size distribution might not be necessarily beneficial for the battery electrochemistry, but in general, it would reduce the viscosity of the suspension. Another example shows the effect of screw speed on the particle size distribution and rheology of an anode paste mixed in a twin screw extruder. The left graph shows that with increasing screw speed, a fraction in the size distribution is shifted to a smaller particle size in the anode slurries. We assume that this fraction corresponds to the carbon black, marked in red here on the SEM image, the extruder can break down carbon black agglomerates depending on the screw design and the screw speed. The right graph shows the viscosity of the sample anode slurries versus the shear rate. The change is in size distribution is visible then in the increase in the viscosity. So the viscosity is not only sensitive to the slurry composition, but also reveals structural characteristics in the slurries. The yield stress of a suspension is the minimum stress that needs to be applied onto it to make it flow. When the sample is exposed to increased shear stress, the measured deformation increases linearly with a slope of 1 in a log-log plot until the yield stress is reached, and then the sample starts to deform disproportionately. The yield stress measurement of the before mentioned LFP cathode slurries are displayed here. The same trend is observed as for the viscosity. The deformation of the slurry with 43% solid content is disproportionately indicated by the slope greater than 1 in the plot throughout the measured shear stress range. This indicates that this sample hardly has a yield stress and is irreversibly deformed at small stresses already. The yield stress gives a hint of the stability against sedimentation during the storage of the slurries, and it also predicts the spreading of the coating after the slot die coating. Thixotropy of slurries predict their coating stability and can be characterized by shear recovery tests. The slurries are sheared with a small shear stress at 0.1 reciprocal seconds until a steady viscosity is measured. Subsequently, the slurries are sheared at high shear rate that mimics the shear rate in the slot die, and then the shear rate is abruptly changed back to the low shear rate. The viscosity plotted versus time allows to measure how quickly the viscosity recovers to its initial value before the exposure to the high shear. The faster the structural recovery, the less spreading and bleeding exhibits the coating slurries. Another way to study stability is a creep test. The slurries are subject to a constant stress and the deformation is measured as a function of time. After a certain time, a linear deformation response becomes apparent. The slope of the deformation versus time, hence the first derivate, is the shear rate. The zero shear viscosity can be calculated as the ratio between the applied stress and the shear rate gained like that. The lower the shear viscosity, the lower the storage stability of the slurry, of course. In the subsequent section, we take a look onto characterization of the dried processed electrodes with rotational rheology. Rotational rheometers can not only be used as a QC tool to check wet slurry viscosities, but also to characterize the viscoelastic properties of dry electrode films. This dry processing is still subject to investigations because the calendering, homogeneous sheets, and scaling up is very challenging. The viscoelastic behavior can be tailored using the right binder system and processing parameters in mixing and calendering. Knowing the viscoelasticity of the film, the mixing and calendering steps can be optimized. Certain viscoelastic properties are necessary to yield a homogeneous electrode film, sticking to the calender roll and being then transferred onto the current collector with the second set of rolls. For viscoelastic measurements, the rheometer must be capable of deforming the sample in oscillation. A typical measurement in oscillation mode is the so-called amplitude sweep, where the material is exposed to a series of stepwise increasing deformation amplitudes with a fixed frequency. This experiment provides information about the general structure of the material. Is it more liquid or more solid-like? The firmness and the stability of its structure. The plot on this slide shows the viscoelastic properties of dry electrode material produced under different conditions. The information that can be extracted from this experiments includes the storage modulus, G prime, which is a constant value at low strain values in the linear viscoelastic regime, and it serves as a parameter for the stiffness. The loss modulus, G double prime, in the linear viscoelastic range, serves as a parameter for the cohesion inside the sample. The critical deformation at the end of the linear viscoelastic range indicates structure breakup and is a parameter for the stability of the sample. In this example, the results of the amplitude sweep test on a semi-dry extruded PVDF NMC cathode films is shown. The material mixed at lower temperature in the extruder, it's the blue curve, exhibits the same stiffness as the one produced at higher temperature, the green curve, but it resists stronger deformation. This is another sample of an amplitude sweep test on a PTFE graphite mixture that was mixed with a twin screw extruder and passed through 1 or 2 mixing zones in the extruder respectively. PTFE is known to form fibrils under shear and acting as a binder in dry processed electrodes. The sample that was exposed to 2 mixing zones in the extruder exhibits a higher plateau value of G prime in the linear viscoelastic regime than the sample exposed to only 1 mixing zone. The SEM image on the right here emphasizes that by using 2 mixing zones, smaller and more PTFE fibrils evolved, and this reflects then in a stronger network between the graphite particles and a higher G prime, but a gradual breakdown with increasing deformation. The fewer and thicker fibrils in the sample mixed with 1 mixing zone presumably withstand greater deformation, as indicated by the drop of G prime at higher critical deformation. So these results displayed show how oscillatory rheometry can be used to characterize the fibrillation and network strength in a dry PTFE electrode film. So summarizing this presentation on rheometry for battery electrode processing, I like to point out that measuring the slurry rheology with rotational rheometers do not only serve as a quality control tool, but also for developing new formulation, especially for tailoring the binder system. And it predicts the performance of the slurries in the coating process. A rotational rheometer can also be used to characterize viscoelasticity of dry processed electrode films in oscillatory deformation. And hereby the stiffness, cohesion and binder network strength can be characterized. And now I will transfer the presentation to my colleague, Alon Vaisman, who will talk about the inline coating metrology. Thank you.
Thank you very much, Annika. The importance of ensuring optimal mixing performance and correct flowability of active materials, slurries, or powders can hardly be overstated. Manufacturing electrodes at mass production scale and with quality required by the end users seems to be one of the most challenging tasks the industry is facing. Research suggests that largest losses of production yield are related to quality issues in slurry mixing and electrode coating processes. This is especially important for the companies looking to enter the market and rapidly scale their production to meet the volumes and stringent quality requirements of the automotive industry. Ensuring the uniformity of the active material loading during the electrode coating process is one of the most critical quality parameters. When the anode and the cathode come together in a battery cell, the ratio of anode to cathode capacity, A to C ratio or N to P ratio, will determine the electrochemical balance and will affect the performance of the cell. Anode to cathode balance needs to be maintained in each point over the entire area of the electrodes, not just on the average. An incorrect N to P ratio can speed up capacity decay and reduce the lifetime of the cell. It can promote the formation of dendrites, hotspots, and in extreme cases lead to a thermal runaway. Close monitoring and tight control over the active material loading uniformity is of increasing importance. But until recently, the tools available to process engineers and quality teams for measuring the electrode loading were limited to single-point or scanning sensors. As the battery technology continues to develop, so does the need for more advanced metrology tools. Conventional single-point sensors only interact with a small fraction of the surface of the electrode, usually less than 5%. Variations in loading on the edges of the coating are difficult to measure, and the time it takes to collect the data for representing a loading profile is measured in multiple seconds, slowing down the ability to respond to process changes. Data available for traceability and failure analysis is also limited to the same small fraction of the product, resulting in potentially non-conforming areas of the electrode, making it into the downstream process and resulting in costly scrap of a complete cell. A new technology introduced by Thermo Fisher earlier this year aims to address these challenges. This new technique, called inline mass profilometry, measures the loading on the entire electrode during the coating process. It captures a complete side-to-side loading profile every millisecond and delivers complete mapping of the entire electrode at full production speeds. To help visualize the difference between the conventional single-point scanning gauges and the mass profilometer, we can use the illustration on this slide. A scanning gauge usually consists of a frame on which the sensor moves from one side of the electrode foil to the other and repeats. The resulting dataset captures sort of a zigzag pattern across the electrode as the coated foil moves through the process. For example, if the line speed is 60 meters per minute and the sensor takes 5 seconds to move left to right, 5 meters of product would have passed until one profile measurement is complete. Areas that do not pass under the sensor are not analyzed, and coating variations or defects could be missed. Mass profilometry, on the other hand, captures the complete profile nearly instantaneously every millisecond. It produces a record of the entire electrode roll and makes the information and the results available in real time to help make process decisions and monitor quality. Mapping the entire electrode enables one to get a better understanding of the coating process performance. Edge features are analyzed in greater details, and it becomes possible to identify spot defects like streaks, divots, high or low loading spots. The example screenshot here from the mass profilometer HMI shows 2 patches of NMC cathode. This data was collected at 60 meters per minute line speed. Mass profilometry data makes it easy for the operator to see that the loading is high and out of spec on the bottom right section of the lower patch. A closer look also reveals what appears to be a streak in the machine direction, in the vertical direction. The software is able to calculate statistical variables like average, maximum, and minimum loading in grams per square meter, and transmit this information in real time to the plant control system. Special features enable the user to focus on multiple areas of interest, like the patch edges, for example, and easily identify and trace non-conforming area to the specific position on the roll. The example on this slide is a good way to consider the difference between optical inspection and mass profilometry. Image from an optical inspection system on the left looks at the surface of the electrode, and in this case, the algorithm did not flag any abnormality. Mass profilometry mapping of the same sample shows clearly that the darker areas in the image are actually areas where the loading is too high, indicated in red. Additionally, the vertical streak of high loading is clearly identifiable in the mass profilometer data, while it is completely invisible to the vision inspection system. Mass profilometry makes it possible to identify spot defects on a millimeter scale and understand if the defects result from excess mass or insufficient mass. You can see on the left an example of both types of defects on one electrode. Coating edges can be analyzed to a greater level of detail to understand the behavior of the coating process over time and see if the loading on the edge is within specifications. Being able to analyze the distribution of active material on the entire electrode as it is being coated gives one the ability to make quick adjustments and tune the coating process. The example here shows a variation in loading between the left and the right side of the patch. You can also see small vertical streaks that are actually visible in the photo of the same patch on the right. If you look closely at the light reflection on the top and the bottom center of the area, you can see these streaks that are represented as green and blue vertical lines on the mass profilometry data. This confirms that the measurement itself produces a real measure of mass loading variation on the patch, which can be confirmed by sight. Ability to tune the process on the fly can be valuable and help speed up parameterization and validation of a new process. In addition, one should consider the cost of scrap that is produced during startup activities and initial process qualification. In the example here, the operator makes a change to the process to correct to correct for low loading regions. But in doing so, they create a problem on the edges of the patch, where the loading becomes too high. Without an in-process analyzer capable of detecting these variations, the user would have to rely on laboratory sample tests that can take many hours to produce, and in the interim, could result in the production of a large amount of out-of-spec material. To emphasize the unique capability of mass profilometry for detection of loading defects, we performed an experiment where a sample of NMC cathode was measured, and the mapping of it is shown in the bottom left corner. We then took a few flakes of the same cathode material and placed them manually on top of the sample. You can see these flakes in the middle. They range in size from approximately 1 to 5 millimeters. We then measured the sample with the flakes on it. Looking at the photo of the electrode on the top, you can see the larger flakes with some effort. The smaller flakes are much harder to see. There is no color contrast, and the optical inspection system would struggle to detect this type of a defect. The mass profilometry data, however, makes the flakes easily detectable. The difference in mass in the local area where the flake is placed is very large and is easily picked up by the system. I'll spend a few moments on the integration of mass profilometers into electrode production lines. The platform is a modular one and allows the user to configure one or more analyzers in a synchronized system for various coating line configurations in wet or dry electrode production. In addition to being used for inline metrology, the system can be equipped with an offline sample stage and used for testing discrete samples at line or in laboratory settings. To summarize, as the technology for battery manufacturing continues to develop, so do the production analytical tools. Extrusion technology can help develop and scale up new formulations faster. Having a tight control over rheology and viscoelastic properties is critically important for quality. The new inline mass profilometry technology enables greater process understanding and continuous inline quality assurance to help battery manufacturers reduce costs and have a greater confidence in the quality of their products. Thank you very much for tuning into our presentation. We can now take a few questions.
Hey everyone. So thank you all for the presentations. Thank you, Alon. Thank you, Annika. So I am Jay Anye. I'm a Senior Business Development Manager at Thermo Fisher Scientific, and I will be the moderator for the Q&A session. So please continue to put your questions into the chat. We've already had a few roll in while the presenters were speaking, and I will try my best to answer them one at a time and have the presenters give you concise answers. So to start, Annika, let's start with you. The first question that came in is on the rheology. So how would you go about reducing the slurry viscosity to a minimum without changing the solids content?
Yeah, as you've seen in my presentation, reducing the size of the particles in your slurry would, in principle, increase the viscosity. But if you are able to broaden the size distribution, you reduce the viscosity. However, I think most of the time this is not desired to change the size distribution of the active material, mainly only of the carbon black. Another way to reduce the slurry viscosity or ensure a low viscosity is to have the correct binder concentration so that all particles are then kept in a good suspension and not agglomerating. And with ensuring that you have no agglomerates, but small particles separated, usually also you reduce the slurry viscosity.
Wonderful. All right, and the next question that came in is on inline metrology. So Alon, if you'd like to answer, the question is, can you measure multiple layers of coating using the mass profilometer?
Yes, thank you for the question, Jay. Mass profilometer is measuring the total mass of the sample that is introduced into it. The technique is based on X-ray attenuation and will provide a result that reflects the total mass of the sample inspected. For cases where measurement of multiple layers is required and a differentiation between mass of each layer is needed, multiple systems can be synchronized in on a production line to provide a measure of total in each location, and using these results, compute a differential mass at each coating area. This is specifically applicable for multi-layer coating and also for double-sided coating applications that are common in the battery production.
Wonderful. And then Annika, the next question is to you. So how can rheometers provide insight into the distribution of the slurry components?
Could you repeat that? Sorry.
Yeah, how can the rheometers provide insight into the the distribution of your slurry?
You meant the distribution of the particles in the slurry, if that
Exactly.
is meant. You would see, for example, if you have agglomerates, especially at the low shear range, a higher viscosity. If you have agglomerates, and if you have a good distribution of your particles in there, it would reduce then the viscosity, especially at the low shear rate end. Yeah.
Okay, excellent.
Hope that's answering the question.
Absolutely. And then Alon, this next question is for you. Is there a limit on how fast the coating line speed can be for inline metrology?
Yes, thank you, Jay. The specification of the mass profilometer is limited to 120 meters per minute of line speed. However, the practical limit does not really apply and is only important in a sense of the desire of the end user to receive spatially accurate information. Increasing line speed beyond the specification will result in machine direction compression of the pixels, so to speak, and will somewhat distort the image, but would still provide valuable data to the end user.
Wonderful. And then going back to the rheometry, so Annika, for you, my question is, thank you for the presentation. Is it possible to assess the quality in line in the extruder, for example? So can we, basically assess the quality in the extruder or in process?
I wouldn't say inline, but at line. If you collect a side stream of your slurry and then press it through a capillary, measure the pressure drop along the capillary, you could do something like capillary rheology while you are mixing your slurries in the extruder. And this, I know this is available from Bühler. It's called Qualib. It's a measuring tool.
So Alon, one question for you on the Linspector Edge. So or the inline metrology specifically, how do you get data out of the system?
All right. The system is capable of communicating with plant control systems using typical industrial protocols like OPC. It is possible to transmit data in real time, both the variables and, if required, the complete mapping of the electrode as it's being scanned. In addition, there is a way to configure user-specific custom reporting options using a REST API communication interface. The system is capable of storing recorded data on board the device for approximately 2 weeks of continuous operation. This helps retain the most critical and fresh production data in an easily accessible format, and also the user can decide which of that total information they wish to historize in their production traceability systems.
Okay. Wonderful, wonderful. Thank you, Alon. So the question for you is, how does the moisture content impact the viscosity of the slurry? So there's water content.
I haven't made measurements of or comparative measurements of moist slurries and dry slurries, or let's say slurries that had been processed in dry conditions. But in general, I heard that the moisture could increase the viscosity, as it could lead to gelation or network formation in the slurries. Haven't confirmed it though.
Okay. And then I assume that would probably lead to some kind of cell performance issues as well when you get too much.
Yeah, definitely, and you might not be able to coat it.
Right. So as you increase your viscosity, this kind of increases the conductivity, is what I believe the person is asking. how does this impact your, or I guess, how can you measure that using the rheometer? Are you able to kind of measure the impacts on conductivity and viscosity?
Yeah, I wouldn't say that viscosity and conductivity are 100% connected. You could have a low viscosity and having then a high conductivity of your slurry once it's dried. So I wouldn't say these two things are completely related.
Okay, no,
Yeah.
that's fair. And then the next question that's come in from the audience is on the thickness of the anode and cathode coatings before drying and after drying. Alon, this question might be more for you.
Yeah.
So what would you say is the optimum thickness of the coatings before
I can try and
drying?
take that, Jay. The thickness of the anode and cathode is specific to the battery design, and each manufacturer tends to have their own. Typical values that we see in the industry range between 50 microns to maybe 150 microns for both anode and cathode. But there are, of course, different and unique batteries that are being produced. There isn't one size fits all that we can state as a typical thickness.
Okay. Very good. And then Annika, going back to you, for the rheometers, so can the rheometers with air bearings be used in a glove box with argon in the atmosphere?
Yeah, actually we checked that, but then it's not an air bearing. You have to connect an argon supply to the measuring head, and it works. Yeah.
Okay, wonderful. Wonderful. All right. And then it looks like there's one more question in the chat. Also back to you, Annika. So when showing measurements on solid contents and process parameters, would you be able to spot defects in the electrode that could, impact the performance of the cell?
Not absolutely. I mean, if your slurries are out of spec, then it would also lead to bad coating, and then you would have defects in your dried electrode later, and then also bad performance. But a bad performance can also come from other things, like the coating process could be bad, and then you have cracks. It doesn't necessarily mean that you have a bad distribution of your binder, and that you would see that in the rheology.
Great.
Yeah, but at least it is an indicator.
Great.
And therefore it's used as a quality control tool very often.
Okay, wonderful. So it looks like that brings us kind of to the end of this session. So I just want to thank Alon and Annika once again for your wonderful topics and presentations on rheology for QC and inline metrology. So thank you both. And if there are more questions in the chat that come in later, feel free to put them in, and then Alon and Annika can do their best to get back to you in a timely manner. And that will wrap up our session for today. So thank you all for joining.